All right, good afternoon. How is everyone? We've got a small crew today.
Good. How are you, Professor?
All right. So several announcements before we get into any questions. Number one, homework 2 has been graded. However, the ability to transfer it from GradeScope back into Canvas is currently not working. So your homework is graded. You should be able to see it. The stats are up there, but we haven't quite got it linked back to Canvas. We filed a ticket with Campus to fix that. Let's see, what other questions? There were lots of issues with homework 2, in particular related to the switch question that maybe I'll spend just 1 second talking about. So the idea on homework 2 was that we were looking at ways of measuring the resistance. And in particular, let me bring up homework 2 so that I can exactly say this. We were trying to design switches, okay? And so the idea was that we were going to use a MOSFET as a switch. And so one of the things that we were asking you to drive is that this is not an ideal switch. And so the switch is going to have some resistance. And so what we wanted to know was what was the on resistance of this switch, okay? And there were a lot of students that immediately said, well, it's 1 over GM. And I can only assume that that's the case because we talked about this diode connected device. And when we do look back into this device, it's very true that we see 1 over GM. Okay. Here, that's not the case though. You know, we're taking this either to VDD or to ground. This is one side of our switch. This is the other side of our switch, okay? And so the impedance that we see looking in here, it's not 1 over GM, okay? And so it turns out that fortuitously, you could actually get the right answer or part of the right answer or close to the right answer on homework 2 using 1 over GM. However, you'll see that you lost points for this even though you had what looked like the right answer. This is a case where if you come up with the answer but the approach is wrong, you know, we're going to take off points, and it reflected on this particular problem. So it's important to remember that this switch is in triode. And so we need to use the right equations when we're trying to solve this problem. And in particular, the TAs told me that there have been a lot of confusion and a lot of misuse of the IV equations in the wrong region of operation. Okay, so just make sure that if you're in triode, which is satisfied by looking at VDS and VGS, that you use the triode current equation. And if you're in saturation, we use the saturation current equation. Are there any questions about this particular problem? Okay. Couple of other comments to discuss. You know, one, on the homework in general, I would probably try to start with the cadence problems first. You know, today, this afternoon, there was a lot of questions on Piazza, and it's very hard for the TAs and myself to answer these questions, myself in particular, because I'm lecturing to you right now when homework is due in an hour, to answer any questions on Piazza when it's this late. There's just not much room for us to even have the ability to help you. It's not that we don't want to help you, it's that we literally cannot help you. So my recommendation there is to prioritize doing the cadence problems first. This way, if you do need help from the TAs, you have the ability to go to their office hours, my office hours, and then the rest of the problems, you know, you probably can do towards the end at the last minute, should you attempt to do that. But I will caution you that these homeworks are long and it's very difficult to finish them at the last minute. All right. let's see, other questions. I guess from you guys, are there any questions related to material in lecture? So I will say that I've taught this class many times, and there are often many questions during lecture. So it's a little concerning that there are no questions right now, and I'm a little worried that you guys aren't either watching them or taking advantage, or you do have questions, and this is going to get reflected next week on the midterm. So please, if you have questions, now is the time to ask them. This is meant to be more interactive, and I don't want to turn this into another lecture. Okay. All right. Well, then that'll bring us to our next topic of discussion. Maybe. All right, so next week we're going to have the midterm. The midterm is going to be at this exact time, 4 p.m., and it's going to be over Zoom. This is going to be my first exam, proctoring an exam over Zoom, so it's a little bit of an experiment for all of us. However, I've done what I think is best to make this go smoothly. There undoubtedly could be a few hiccups, and we'll hopefully work through them together. So on Canvas, I've posted, I don't know, 3 or 4 previous exams to give you guys a sense of what to expect. I will say that this particular exam is a little bit longer. So to keep that in mind, that some of the material may be slightly differently paced, and or the exams are a little different length. Your exam will only have 3 problems. It'll have 10 true false problems, and then it will have 2 long answer questions. I've also changed the policy. Typically, I do closed book exams where I allow you to have 1 cheat sheet where you can write equations on both sides. I don't have any fair way to police that this year or enforce that in any sense. And so I'm just going to make it open note for everybody such that we're all kind of on the same footing in that regard. We will still have 80 minutes, and then there will be 10 minutes at the end to upload your solutions. Okay? But I want to be very clear about this. It's a lot like the homework where if you submit it late, it's late. So you have those 10 minutes to upload your exam. If you choose to use 5 of those minutes to try to continue to work and then cut it very close to try to upload your exam in the last 5, you might run out of time uploading your exam. Do not waste those 10 minutes. Those extra 10 minutes that I'm giving you are not to continue working. They're to make sure that you get your solutions uploaded so that we can grade them. All right, so format of the exam, there will be 10 true false questions. There are questions that look something like this. The capacitance of a p-n junction decreases as its reverse bias increases. You simply need to write T or F. That's it. No justification. You don't need to tell me why. You don't need to tell me caveats or weird corner cases. It's true or it's false. Okay. And very importantly, in previous years, I will get some interesting letters. And so when I say interesting, I will get things that look like this. Okay. These kind of hybrid T's or hybrid F's with kind of long tails where you're not quite sure if it's a T or an F, or some people will scribble or write cursive so that I can't quite tell. It's got to be very clearly marked T or F. Pick one. Okay. The other thing to mention, and I just want to point this out again, is that incorrect answers are -1. So the entire purpose of this true false question is that I can cover a lot of material and that we actually are assessing whether or not you know the material, not guessing. Okay, so true false is a little too easy to just yes, no. You lose a point if you get the question wrong. Okay, you don't lose any points if you don't answer a question. And so all that this is meant to do is make it disadvantageous to you to guess on these problems. If you don't know, you're much better off leaving it blank rather than guessing. I do capture this. I do cap your score at 0 points, so you can't get negative. I will say in the past, there have been many exams that were very negative. Try not to do that. I would, only mark them down if you are sure one way or another. All right, and then there are just going to be 2 questions that are going to be a little bit more in depth about one particular problem in the material. For example, I think that we did this one a few weeks ago where we calculated what the transconductance is of this device. We calculated the output impedance. We then derived an expression for the transconductance efficiency. And then we did the same thing for a MOSFET and kind of went through this. You'll notice that the problems are structured a lot like the homework where there's kind of A, B, C, D, E. A little bit different than the homework. I try to make the problems decoupled so that if you mess up on A, it doesn't carry forward to B, C, D, or E, that you can continue on and still make progress on this. I would encourage you very much to show as much work as possible. We will be generous with partial credit when we grade the exams. And very clearly box your answers when you're done. Normally, I would have you fill out this sheet and only write your answers here. It's a little different in the sense that I assume that most of you, like myself, don't have printers at home. And so you're going to be doing this on blank white paper. That's perfectly fine, and that's a very reasonable way to upload it. Just make sure that at the end, 2A, we have an answer, and there's a box around the answer so that we know what to grade when we're going through this. All right, and then, this particular exam, to be honest with you, was on the longer side. It had 4 problems. It was a little too much given the time constraint. Some of these problems will look familiar. If you've actually looked at homework 4, I gave you this problem on homework 4. And I think I also gave you this problem on homework 3 or on homework 4. So I often recycle exam problems and later turn them into homework. So you've been preparing for the exam, whether you realize it or not. The one thing I will say is that the 80 minutes often surprises people. As well as the solution. So, against my best judgment, I get asked every year to post the solutions. I really think that it is in your best interest to go through the exam and try it yourself without the solutions present. This tells you where you have gaps in understanding and need to focus your efforts. Whereas if you just directly look at the problem, spend 2 seconds on it, and then go right to the solution, oftentimes what I hear students say is, oh yeah, that was easy. I know how to do that. When in fact, if you had to do that same problem in the time constraint, you wouldn't have known how to do that. You wouldn't have been able to do that. I hear this very often, and so I hate releasing the solutions, but I know that students really like them for study guides. So I came to what I believe reasonable compromise this year. I gave you the exams last week, and the solutions will be released today after class. So you'll have a week with the solutions, but hopefully you've at least looked at some of the exams without the solutions ahead of time. Lastly, the other thing with the exam, I want you to upload your student ID or a picture ID. I will use this to compare against the Zoom screenshot just to make sure that, you are who you say you are and you are taking the exam. Are there any questions about the exam?
I had one question about that ID thing that you were talking about. So can we actually upload those earlier, or do we upload those in those 10 minutes as well?
Yeah, so at the end, what I would do is just, you're going to have a page that has your name on it. I would just leave 3 or 4 inches at the top so that you can take a picture of your ID on the first page and upload that with it.
Perfect. Thank you.
And then there was a couple comments in the chat about 5 minutes to upload your solutions. I'm actually going to give you a little bit longer. I talked to the TAs today, and they said it is possible to upload it in 5 minutes, but it was a little too stressful for them and they felt frantic. And so they said 10 minutes was appropriate. So yes, the exam will be 80 minutes for the actual exam to do the work and then 10 minutes to upload. All right, other questions? Let me also very quickly, while I'm just sharing the exam, also show you what the solutions will look like so you can see how to read them. Oh, this is a bad one. Too many windows. What a disaster. All right, let's try this one more time. Here we go. All right, so here are sample solutions. This is for the 2016 midterm. You'll notice a couple of things that I just want to explain when we look at the solutions. First off, there are going to be multiple versions of the exam. And you can see here that, the A versions are the pink answers, the B ones are the green answers. And if it's common between the A and the B exam, it's yellow. You'll notice that on the front of the exam, it will have the version that you're looking at. I typically upload the A version, so all of the pink and the yellow are the solutions that we have here. Importantly, one thing that I do want to point out is that, I don't have super detailed solutions to the exam. They're not like the homework that are 30 pages. The entire solution to this exam fits on 1 page. My exams or my solutions are very, very abbreviated. They're to the point. I usually list kind of key equations and then go right into the solutions. They're not step by step where you can follow them to understand what's going on with the problem. All right, any questions about the exam, logistics, how we're going to do this?
How are we going to actually get the exam? Is it going to be released on Canvas? Or what's the plan for that part?
That's a great question. I don't know the answer yet. I'm actually trying to figure out how to do that right now. I think that it's going to be on Canvas. I think that what will happen is that at 4 p.m. next Thursday, or next Wednesday rather, you will receive on Canvas a link that lets you view it. And maybe I'll start it a little bit later, so I'll skew it to something like 4:05, such that we get a chance to get on Zoom and everybody's kind of here at 4. But I believe it'll be on Canvas. Other questions? Oh, I guess that I should also comment very quickly on what material will be covered on the midterm. It'll cover everything through lecture 7. So everything that's posted right now will be on there, but anything after this week won't be considered material that'll be on the midterm. All right.
Just one more question.
Yep.
So we're gonna meet in this Zoom link, correct?
Correct.
Or a different one?
This one.
Okay.
Yeah, and you all need a video camera so that I can see all of you and not just pictures of your puppy. All right. One other thing, and then I'll go through one example that I was going to talk about today. I did make a couple of adjustments to the syllabus, mostly just to move around kind of dates. One, homework 4, I'll talk about it in just a second. It is out now, but rather than being due next Wednesday, right when the midterm was going to be there, I pushed it back a week. And so you'll notice that now you're basically going to have 2 weeks for each of the homeworks that are coming up. So homework 4, 2 weeks, homework 5, 2 weeks exactly, actually, and homework 6, 2 weeks as well. Next Thursday, I will also have Zoom discussion, but it will be on Thursday rather than Wednesday, since we're going to use the midterm on Wednesday. I'm going to talk about simulating differential amplifiers then, and I will also post the project and spend some time talking about the project. Notably, you'll see that you have a little under a month to work on the project, and the project is a pretty significant portion of this class. It is absolutely not something that you can do in a weekend before it's due. So, if you're not starting and making a lot of progress on the project, even in the middle of November, it's going to be difficult to complete the project. So make sure that you account for that and don't try to push that to the last minute. Other than that, the rest of the course is unchanged in terms of its organization.
So the Thursday class will be live, right?
What was the question?
So the Thursday class, the next week Thursday class will be live.
Yeah, the Thursday is going to be
Discussion
live. I'll send a special link for this 11-5 class. Yes. It'll be live at 11 o'clock. Yep. All right. All right, one last thing, and then I'll go into problem. Come on. All right, so homework 4. Homework 4, we're going to get a lot of problems related to biasing in particular. And so in lecture 7, we brought up this structure that I talked a lot about, and I gave you the solution, and I computed a table for this value here of m. What I'm asking you to do in this problem is to actually do the derivation of this, and then we're going to kind of prove out various different aspects of the structure. Okay, a lot like homework 3. I think that one thing should be very obvious quickly is that if I have the same current, through both of these devices, and the gates are tied to the same voltage, okay, it should be immediately obvious that they can't be in the same region of operation, okay, because the sources are not tied together. And so that means that one of these devices or both of these devices are going to be in triode, and only one of them can be in saturation. And so you need to think a little bit about which device that is. I think that if you look carefully, this diode connected device gives you a pretty big hint, but there's other ways to kind of prove this, and hopefully after homework 3, we have a good sense of Problem 2, so here we're looking at a source follower. This is something that we talked about in lecture 6. We're going to be looking at some interesting things related to the output voltage swing, the small signal model, and then what happens when we play with the body of this device, tying it to different potentials. And then we're going to come back and we're going to look at current sources or current mirrors. These are topics that were again introduced in lecture 7. We're going to play with a little bit of an interesting deal here with this resistance. And then we're going to do a transimpedance amplifier. This one again was from the midterm that I showed you previously. We're going to do some frequency response and we're going to calculate the small signal transfer function. All right, and then the last problem, the cadence problem, you're going to design a reference circuit, in this case a constant GM, and then we're going to do a sweep over temperature. And so we're going to change the temperature from -40 to 130, which is quite a bit, and we want the supply to vary by 10%, so 1.8 plus minus 10%. And then you're going to design the circuit and show us through simulations that your circuit meets all of these specs. Okay, and so you're going to need to look at how to sweep temperature and cadence, and we're also going to need to know how to sweep the supply voltage in cadence. That brings me to one other point. There have been a few issues with cadence, in particular CLS admin tool, the tool that we use to unlock files that when we inadvertently close a session. I have filed a ticket with campus IT and they're finally starting to make progress on this. I hope that within the next few days, we should have this resolved once and for all. All right, so I wanted to come back in and I wanted to look at one of the circuits that we talked about during the lecture and spend just a little bit more time kind of thinking through this lecture. So we looked at a few different ways of making reference voltages. So we started off using this particular circuit and we use it as a current reference. That is that we generated a current, I out, that was proportional to this resistance. However, one of the things that we did not like about this circuit in particular was that if VDD changed, we saw a direct perturbation in the output current, okay? And so, we'll quantify this a little bit more directly later on in the course, but this is what's known as the power supply rejection ratio, or PSRR. And so this PSRR, it essentially quantifies how much perturbation in the output we get for perturbation on the power supply. So oftentimes when we're thinking about amplifiers in particular, we are applying a small signal input and we are measuring the small signal output response. In this case, what we're doing is we're leaving the input fixed. That is, we're setting the input to some nominal value. And we're going to apply a small signal stimuli on top of the DC power supply. And this is how we're getting what's called the power supply rejection ratio. So we're going to simulate this for amplifiers and bigger kind of structures in a few weeks. But the concept already applies right here. And it's pretty obvious that if this power supply was moving around, it's essentially modulating the current that's flowing through this node, which this transistor is then mirroring and copying over to here. And so we see this relationship in the output current when we're changing VDD. And so we spent a lot of the lecture looking at ways to make better currents that were less independent. And so one of them that we spent a little bit of time talking about was this idea that is very similar looking, but fundamentally quite different. All right, so we have a structure that looks something like this. We have two NMOS transistors, not drawn very well, but I promise they're NMOS. And we have two resistors, one that we'll call R1, and this one that we will call R2. And so, you know, the question is, how do we analyze this? How do we get the result? And I just wanted to spend a few minutes kind of talking about this particular circuit. And so we know that this node right here, I'm going to call this Vx. Vx is equal to VOV1 plus VT, assuming that M1 is in saturation. Let's call this node Vy. So Vy is equal to Vx plus VOV2 plus VT. And this assumes M2 is in saturation. All right, if I have these two voltages, how much current flows through R2?
I'm sorry, but those equations are valid even if they're not in saturation, right?
They are, but I'm going to use the value for VOV in just 1 minute if they are, assuming they are in saturation. So I'm just preempting my derivation.
Okay.
But yes, VGS is always equal to VOV plus VT. I guess not if they're in cutoff. All right, so I2 is equal to Vx divided by R2, which is also going to be equal to IDS2. That's simply to say that any current that flows through here also flows through here, and no current flows into the gate of M1. All right, so how much current flows through I1? I1 is equal to VDD minus Vy divided by R1. And this also has to be the current that flows into IDS1. All right, so this particular circuit, it's called a VT reference. And it's called a VT reference because if we look in particular at I2, and we said that I2 was equal to Vx, which I wrote as VOV1 plus VT divided by R. And I write out the expression for VOV, which is equal to 2ID divided by KNW over L plus VT divided by R. This particular circuit, what we do is we actually design this part of the equation to be very small relative to VT. So we design through sizing we make VOV2 much, much less than VT. Okay. How do I do that? How do I make this VOV2 small relative to VT? What in this equation can I change? Oh no, my iPad had low battery and it just erased my equation. Okay, I'll rewrite it. So, oh, there it came back. All right, what in this expression right here can I change? So I can't change ID. I can't change KN. What do I have for knobs? I have
Sizing of M1.
I have W and I have L, right? And so I can size this transistor to be a very wide transistor such that I make its overdrive voltage insignificant relative to VT. The nice part is that when I do that, then I can write that I2 is simply equal to VT divided by R. And this is where it gets its name, VT reference, is that we are referencing the current that we are generating relative to VT. Now, the reason why this circuit is better than the previous one that I described is that perturbations on VDD do not show up in the same way as they do in the previous one. The previous circuit, we had a direct relationship. VDD went up by 10%, the current changed by 10%. Here, if you look at these equations and we kind of think about what happens, it will still affect it somewhat, but it's not going to affect it nearly as much, okay? And it's really because we're protecting this VX node and it's being set relative to VT, the threshold voltage, a process parameter, rather than VDD, an external voltage. All right, are there any questions about this circuit or how this works?
So we are just making it a square root function of VDD, right? Then
Yes.
Because ID1 does depend on VDD.
Yes, and so, I mean, you can actually go through all of the math and you can show that depend on how you size M1 and M2, you know, I1 and I2, they can be related, but they don't have to be equal. And that's kind of where this comes from, that VDD can change and I out is somewhat independent. It's not entirely, but it's somewhat independent of that. All right.
So what are the main drawbacks for this design that you would say? I mean, generally there are trade-offs, right?
Yeah, absolutely. There's a couple of things. You know, I mean, your question, I guess, if I was to say, we have a handful of references that, and you know, there's even more than we've talked about in this class. What are the benefits of each of them and why might I use them? This one, you're still sensitive to a couple of parameters. You know, one, it requires an absolute value of R. An absolute value of any component on an integrated circuit is very hard to ensure. And so if you wanted a precise current, i.e. a current that was within 20%, this is probably not the right reference. You'd probably be better served using something like a proper band gap. However, with a band gap, you have additional complexity in designing the rest of the circuit. And so if you were designing a simple circuit and you were just trying to get a mostly independent supply current, I think that this is a reasonable choice. Does that answer your question at least somewhat?
Yes, yeah. I'm just thinking if there is anything else. Yeah, it does.
No, I mean, like if you really, let me switch sharing here. I mean, look, if you're talking about any kind of large integrated circuit, they are not going to use a VT reference. A VT reference might be used in a relatively small design. A large design is going to use a band gap. They're going to use something that looks like one of these two circuits, or even potentially a more complicated or advanced version of it. The reason being very simple, that if you're designing a large ASIC, i.e., Apple's new Bionic processor, it's a very big chip. You want good references. You're going to spend the additional design effort, power, area in order to get high performance out of the circuit. And some of the best performance you're going to get is when you actually relate this to something a little bit more fundamental than just a VT or an R. You'll do something like a band gap, where it's related to a material property, i.e. the band gap of silicon in this case. And that's why these end up being 1.24 volts.
Okay, thanks.
All right, and so during the homework, you're going to design this circuit. You're going to design a constant GM, which is a reasonably smaller circuit. However, we kind of talked about some of the benefits. And in addition to that, you're also asked to design a startup circuit. Okay? And the reason being that we want you to be able to simulate and see what happens to the circuit with and without the startup circuit present. And so oftentimes students ask, well, which startup circuit should I use? There's lots of them. You're free to play around with it and look at it. This one is a relatively good starting point because it's very simple and it's straightforward in its operation. There's other ones that are a little bit different. You can try those if you like. All right, any questions about homework 4, midterm, lecture, anything? All right, well, I'll see you next week. Good luck on the midterm. I hope that everybody does very well. Thanks. Bye.
Thank you.